So, good day everyone. We'll be looking at design of connections, and we'll be looking at three principal connections, which are welded, bolted, and riveted connections. Now, the most common one among the three is this welded and bolted connection. This welded connection, even though it is roughly triangular in shape and in cross section, and this one, for instance, is known as fillet weld, and it is economical. And we have two types of basic weld. We have the fillet weld and the boot weld. Now, there is something we call the leg length. That is, when we want to weld from here to here, this is the leg length, while the throat is from here to here. That's the throat size. Now, all this leg length and throat size is used to determine the throat size. Now, we have the formula for throat size, which is 0.707 times leg length, which is what we have here. So, and likewise from the leg length, we can get the throat size. From the throat size, we can get the leg length. Now, let us go to the importance of this throat size. A finished fillet should always be convex in shape, as we can see here. It has to be convex in shape. Let me see. Yeah, something like this. Now, and the leg length. For instance, if we have a 4 mm leg length, if we apply the formula 4 times cos 0.7, that should give us something like 2.8 for throat size. And then the strength, how do we determine the strength? Now, each steel member, they have their grades. They are classified into grades, and each grade has its own strength. Now, for grade 43, the strength is 215 Newton per minute squared, with what we are going to be using as an example here. So let's say, for instance, we are using grade 43. So if the throat size is this and the leg length is this, then the strength can be determined from throat size times this particular value, which is equal to, we give 0.60 for 4 mm leg length, like that for remaining members. Let us look at an example here. Let's say, for instance, we have a 6 mm fillet weld, and this fillet weld is to be used to join let me say it's we have an angle of 80 by 80 by 8 mm angle plate, and it's to be welded to a gusset plate, and it's to support a design tensile load of 300 kN. Now, if it is welded all round with a 6 mm fillet weld, what is the required length? Now, the 6 mm fillet weld, the weld strength from here is 0.9, as we have determined how, let me see how that one is calculated. Now, the total leg length is the design load all over the weld strength. That the total leg and total length required. Sorry, the total length required is the design load over the weld strength. Now, if we are given this design load of 300 kN and our weld strength is 0.9, then our total length will be 333 mm. However, now for an angle having 80 by 80, 80 by 80, and the thickness is 8 mm, the thickness of the angle bar is 8 mm, but its size is 80 by 80. Now, let's say we want to get the total length. Now, it will be 2 times 80, which is 80 times 80. Now, that's plus 2L, because we are having two lengths now, the vertical and the horizontal member. Now, for a unit length, now to get a unit length, making this the set of the formula. So let's say this is our length. Now will be, we want to get this L out, this L. So easily we can say, okay, the total length minus this all over L will give us L over 2 will give us L. So if we make L the set of the formula, we can get our total our L to be total length, which equals minus, because we take this one and this, we take it to this side, it will be negative minus 2 times 80. Then because we are having total length minus 2 times 80 now, which equals to 2L. Now, to get L, we have to divide both sides by 2. So that way we have to divide by 2 to get this. Now, if we use this formula, we are going to get something like 333 minus 2 times this, that's 160 divided by 2, which is this. Now this is our total length for the wedding. Now I think this one is simple enough. The total length required for the wedding is this. Now let us go to the second connection type, which is bolt connection. Now we will still talk about the weather connection, some other things, because we'll be talking about the tensile capacity and some other things after a while. But let us go into bolt connection and introduce us to it before we go into that. Now these bolt connections, they are prepared for site connection. They are very easy. We have two types of basic bolts that we always use. We have the bearing type bolt and the friction grip bolts. Now let us look at these bolts. You can see bearing type and we can see the friction grip type. If you look at it very well, they look almost very similar, but in terms of strength they are stronger than one another. In the friction grip type, you can see that it's like this diagram will not show that one very well, but it's stronger. This one is stronger than this ordinary bearing type. Let us look at the design of this ordinary bolt. Now I told you the other time we have design strength and different grade of steel. Likewise, we have different grade of bolts. Now for the bolt, we have even though before the major ones are grade 4.6 and 8.8, but recently we have the different grade type. We have the grade 4.6, 8.8, 10.9, and each one differ in strength like that. Now we have shear for each, but acceptable shear for each one based on the grade size. For grade 4.6 is acceptable shear is this, while acceptable bearing is 460. Likewise for grade 8.8, you can see that this one is higher than this. So grade 8.8 possesses greater shear strength, shear capacity than 4.6 grade. So the bearing stress is limited to 460 Newton per mm square for this grade 4.6. Especially when we are connecting grade 4.3 for grade 43 steel. Now let us look at tension capacity. What do we mean by the tension capacity? That is the capacity, the capacity of tensile strength that this bolt can withstand when it's being connected, and it is usually determined by tensile strength and the tension area. Now the tension area represents the area of the bolt at the root of the thread, and so it's less than the nominal area of the bolt shank. I will explain that one better. Now let us look at an example now. If we have a 12 mm bolt, which is 12 mm bolt diameter, the tension area is 84.3. If we have a 20 mm bolt, the tension area is 248 millimeters square. Now this we say tension failure may arise in simple connection as a result of excessive tension in the bolt or cover plate. Now the tension capacity using the simple method is this tension capacity formula. Now this where P substitute T stands for the tension strength, as we said the other time, and the AT is the nominal tensile strength area. The tensile strength area is this. So we'll take an example so that we understand what we are talking about in this particular scenario. Let us look at, given that a column is subject to a design uplift force of 280 kilonewton. It is held down by 4 bolts of grade 4.6 and into a foundation, concrete foundation. What bolt diameter do we require to carry this particular load? Now the first thing we do is that since this 280 kilonewton is the uplift force, now we require 4 bolts that we want to use. Now what we do is that each bolt will carry a quarter of this, which is 20 divided by 4. So we are designing for 70 kilonewton per bolt. Now to do this, we'll calculate the tension area. Now the descent strength is 195, since we are using grade 4.6, as I said the last time. Grade 4.6, the descent strength is 195. The design strength, the design strength is 195. So if we are using grade 8.8, its own tensile strength, design tensile strength will be 450. Now let us go back to what we are doing the lesson. Now the tensile strength, as you know, is 195 Newton per mm square, as said the other time. Now the tension area is the load over the strength. Now this load, since it's in kilonewton, we convert it to newton, since this one is in Newton per mm square. So that is why we're multiplying by 10 raised to the power of 3, then divided by this. We are now having 285. We're having 285 Newton per 358.97 millimeters square. Let me put it this way. So now if we have this 358.97 millimeters square, that's the tension area that we require for this particular boat. Now what we are going to do is that we'll go and look at the boats that will be able to withstand this particular tension area from the table 10.2. Now this table, now you can see the area that each boat can withstand. This one can withstand this 60 mm can withstand this can withstand this, 22 can withstand this, 24 can withstand 353, while 27 can withstand 469 millimeters square. However, our own is 358.97. So if we look at this, we have 353, which is less than 358. So we have to go for a higher one, which is 469, to be able to carry that particular load. So here we are recommending 27 mm diameter boat, and the tension area for 27 mm diameter boat is 469, as stated here. So in most conditions, boats are loaded in shear and failure, and failure can take place in two possible ways. Failure can take place either by shear or by bearing. And we have a table here, this table 10.2, which is showing us different boat diameter, their tensile area, the tension capacity, and the shear capacity and the bearing capacity. So this is like a all-in-one steel table, as we could see the other time in this other it's a combination of these two. So that is all about that, and that's how to know the number of boats that is required. The next thing is looking at this. I said this is a combined table for all of them, which you can always use. Now this is an example of failure by shear. You can see it here, that the member is trying to slip away from each other here, and the boat is trying to shear along this area. So this is a single failure, or single shear rather. So now there is something we call the shear capacity, which is the shear strength times the boat area, as I said the other time, according to BSAP 950. The shear strength and the boat area, they are both calculated. However, if it is for double shear, that is double shear failure, the formula is this. And there's something we call the bearing capacity, that is, which I've explained the other time too. The formula for bearing capacity according to BS 5950 is bearing strength and boat area times the plate thickness. Now this is your bearing strength, this is your boat diameter, and this is your plate thickness. Now using this formula, we'll be using it to do some calculation. Now if we have a connected part, now that is when we have connected parts, members connected and we want to calculate the bearing capacity of the connected parts, we are going to use this particular formula. Now, after using this formula, PBS, which is the bearing capacity of the connected parts, is equal to KBS times DB times PBS times TB. And I've already explained the DB, which is the bolt diameter, and TP, which is the thickness of the plate. Now, however, after doing this calculation, we will now check whether it is less than 0.5 KBS, ECP, KBS, PBS, where KBS 1.0 for bolts in standard clearance hole, while the PBS is bearing strength of the connected parts, and E is the end distance. Now, let us look at an example. Let's say we have a C grade, as we the other time I was talking about grade 43. Now the grade 43 has been modified to S275 in the recent code. So, and we also have different classes, S355, S460, and other grades like that. Now we have the bearing strength to be this. Now